Good morning, good afternoon, good evening, wherever you're joining us today for this webinar. My name is Shruti Shivdasan. I am the chair of the SUT Plus Aberdeen branch. Before we start, I'll give you a quick overview of SUT. We are the Society for Underwater Technology. We bring together people like yourselves and organizations who have a passion for anything that goes in the water together. And I am part of SUT Plus. The SUT Plus is the subset of the Society for Young Developing Professionals. So we cater to students, fresh graduates, people with a few years experience in the industry, maybe who have had a career change like myself. And our aim is to increase the knowledge of our members through different events that we organize that would be different from what you would learn in your traditional job in the office environment. We are quite active on social media. We have a few places where we are present. So on our website, www.sut.org, you'll get listings of all the events that our branch organizes, as well as all the other global branches. And our LinkedIn page, SUT Plus, has the most up-to-date information. So any updates regarding previous webinars, site visits, you'll find it there. If you have any questions regarding this webinar, any questions or things that you would like to see us do, please send us an email at sutplus@sut.org. And I quite like the YouTube channel because it has a wealth of information. If you're new to the industry, you want to learn about topics like offshore wind, hydrogen, floating solar, umbilicals, go to the YouTube channel because you'll find recordings of all our previous webinars there. And if you're a corporate company, you are keen to sponsor us so that we can continue having these events, please send us an email as well. And if you'd like to support us, consider becoming a member of the society. It gives you discounts on the courses and publications that we have. And lastly, before we start the presentation is going to be recorded. So during the presentation part, kindly mute your microphones and turn off your video because it eats into the bandwidth. And we have two options at the bottom of your Zoom screen. So one is a chat function and the other is Q&A. Please ask your questions using the Q&A function. It's easier for us to monitor one place, and Daniel will answer them for you at the end. And without further ado, I will pass my virtual mic to Daniel and let him tell us more about this energy storage solution.
So thanks for the introduction, and thanks for having me. Really great to be presenting this to you all. I'll just share my screen. Yeah, okay. So my objective with this is to give kind of a very broad outline of what we're doing with energy storage, a bit about the why, and then of course the how. This is going more into the technical stuff, and then talking a bit more about our subsea endeavors. Even though we're a startup that's primarily coming from like a wind energy background, so the subsea space is of course very fascinating, and yeah, I'll touch on this briefly. And very curious to hear any comments or feedback about this technology. So just a quick intro of myself. I'm Daniel. I'm one of the co-founders and CEO of FLASC. FLASC is a spin-off from the University of Malta, where I'm originally from the Mediterranean, and small island surrounded by the sea. So of course that's a big source of inspiration for us. But when we did kind of spin out the company from the university, we set it up in Delft in the Netherlands, where I'm currently based. And this has kind of brought us closer to the North Sea supply chain, and where most of the kind of energy transition offshore is happening. So that's a bit about my story, and now I'll dive into kind of the problem that we're trying to address with this technology. So as you may know, I mean, renewable energy is of course a big part now of what we do when we talk about the transition of the energy system and how we need to decarbonize. And we of course want to rely more on nature for our energy source, but this introduces the challenge of variability. So renewables are depending on the availability of wind and sun and other resources. And yet we still expect the lights to come on when we flick the switch. So we expect an energy, our energy demand is kind of, what we need, and we expect energy to be available when we need it. So this, of course, introduces an interesting challenge that kind of renewable energy supply and demand do not match. It's a very oversimplification of this, but this is really the overarching problem that we're trying to address. We see a bit more kind of specific pain points. So for example, with utility scale renewables, what we mean by this is like large scale offshore wind farms. These are kind of being challenged to have to accept more market volatility and more issues with like negative pricing due to congested grids and all that. And then kind of looking at heavy industries, oil and gas, primarily, that is being pressured by both kind of government and political decisions to decarbonize, but also by shareholders and public pressure in general. Decarbonizing offshore assets in particular is challenging because, okay, you need clean power, but you also need reliable power. So it's very interesting to see projects like Hywind Tampen being done by Equinor in Norway. And yet it kind of also raises the challenge of like, how far can we penetrate with variable renewables until we need storage? And then when we need storage, what are the technology options that can be deployed without introducing new safety risks or without taking up any precious topside space? And then finally, a bit closer to home for myself, as I said, from a small island in the middle of the sea, we understand like what it means to have a congested grid. Especially when it comes to introducing variable renewables, if the grid is already kind of isolated, and even though there is a grid connection to mainland, that still introduces bottlenecks. So when we talk about decarbonizing these types of islands, there are very specific challenges, and these are then compounded by the fact that land is always at a premium and is kind of very expensive and or just generally unavailable. So these kind of specific pain points are what we're trying to tackle with our solution. And before getting into the technical stuff, just kind of talking a bit more about our strategy with energy storage. So the first thing we identified was that we think the marine environment will be a key part of generating our renewable power. So our question at the time as kind of academics, this was my PhD thesis, was like, okay, we can produce power from the ocean, but can we also store some of that power in the ocean? Again, I think coming a bit from our small island mentality, where we look at the sea for everything, like food, energy, and all these resources. So it was kind of a natural question for us to ask. And then, of course, we'll get to how we do that. But this is really our philosophy. So if we're deploying large quantities of offshore wind, can we also, co-locate part of that space for storage? And then, so this is one way of looking at it. It's an offshore technology. It's designed to be deployed offshore, but then there's a more kind of technical way of looking at it from a timescale perspective. So I want to take a little bit of time just to explain the different timescales of energy storage and what we mean when we say like short duration, long duration, and then hydrogen, and how do all these things kind of come together. So this graph, it's from a DMV report, which basically the technical term is like residual power, but what's on the y-axis is basically supply-demand mismatch. So it's the difference between what's being supplied and what's being consumed. And this is a key aspect because it drives the need for energy storage. And then on the x-axis, we have like the different time scales. So what this means is, am I kind of, do I need energy in the next hour? Do I need it tomorrow? Do I need it next week or next month? So this kind of relates to how long does the technology need to store the energy for? How long does it need to discharge it? And within this kind of time scale, as you can see, there is a peak that was already present in 2015 that is kind of on the multi-hourly time scale, roughly almost 1 day. So that's the period of time across which we need to shift the energy, in simple terms, like charge in the morning, discharge in the evening. And then as we look at the 2050 scenario, even with different levels of renewable energy integration, this peak becomes stronger, and then we get another peak emerging on the kind of like monthly scale. So that means charge a system in spring and discharge it in summer, or across this time scale. So when we look at technologies, then we have this kind of categorization that we're seeing. So sub 1 hour, this is what is typically referred to as short duration storage. And we see primarily lithium-ion batteries. I think that's the most obvious thing, and probably what we think of first when we think about energy storage. And then on the longer side, like really kind of long-term storage, we start to hear about storing energy as molecules. We hear about hydrogen power to X and all of these kind of other interesting things that are maybe a little bit less developed than the lithium-ion batteries, but I think are very quickly catching up because they're going to be a key part of the system. And yet it leaves this kind of interesting gap, this slice between this, short sub 1 hour and the, let's say, like kind of weekly or seasonal storage, which we as FLASC, I have to say, as a startup, we've had to kind of really pitch that this gap exists, because we've been challenged a lot about, like, okay, we have batteries, we have hydrogen, why do we need anything else? So at the end of last year, the consulting firm McKinsey did us a big favor by issuing kind of a seminal report, very detailed, in kind of justifying that, listen, there is this gap. Yes, we have batteries. Yes, we have hydrogen, but there's still a key slice in this energy storage problem that is not being addressed by either of these technologies, for which we need other solutions. They've given it a name, so it's what we sometimes refer to as long duration storage, and kind of an indicative time range. So anything between like 4 to 150 hours is now being referred to as long duration storage. So our technology fits kind of within this gap. Sorry, I skipped a bit ahead. So it fits within this long duration technology space. There are other solutions. I'll share some of these other solutions in the technology landscape, but this is primarily like where we see compressed air, pumped hydro, thermomechanical solutions, liquid air, all sorts of kind of like interesting and innovative solutions that are going to be needed to satisfy this gap. So I've spent a bit of time on this just to kind of justify where we are in the space. So we're not really comparable to batteries or to hydrogen, just because the energy system will need a range of technologies to address the whole energy storage timescales. So one thing that we're always challenged about is like, why store energy at sea? What's the benefit? And why not just put a battery on land or put a long duration storage compressed air on land? Well, what's the benefit of having also offshore energy storage technologies, much like we have land-based renewables and offshore renewables? So one thing we're seeing is that in new generation projects, such as, for example, in the Netherlands, there's already a challenge being posed to developers that they are exposed to more volatility in the market. And this is expected to increase. So already in certain offshore wind farm tenders that are happening this year, for example, there are criteria where the government or the legal entity issuing the tender wants to see developers think about innovation, think about what kind of technologies can be deployed within a wind farm or within the same wind farm project that contribute flexibility, to basically allow the energy that is produced by the overall project to be decoupled from the availability of wind in this case. So we see that there is really a benefit, and then the ability to co-locate within the same wind farm footprint implies that we're just maximizing the use of the same space that's already been given as a concession to be developed. I mentioned this as well, but yeah, it is a key aspect. So small islands in sensitive regions will benefit from deploying storage offshore, much like they benefit from deploying renewable systems like offshore wind or floating solar. So this has, I think, kind of obvious benefits. And this is something that we're already seeing as being quite, when we talk to potential users, they understand this very quickly and they see this as an interesting application of our technology. And then, yeah, the other subset, I already kind of mentioned this a bit, was like, we say heavy industry in general, this is kind of oil and gas. So coming back to projects like Hywind Tampen, where you have offshore generation, offshore consumption in an isolated space, you do need some storage if you're going to really make an impact on decarbonization. And then your technology options, when it comes to marinizing land-based, like batteries, there are some challenges with that when it comes to upscaling. So we can, of course, deploy batteries subsea or on vessels, but when it comes to like utility scale, we're talking about 100 megawatt hour plus, that starts to become rather cumbersome as a solution. And yeah, green hydrogen, this is very often perceived as a competitor to what we're doing, but go back, that's why I spent some time on the timescale problem. So green hydrogen and what we're doing with long duration storage offshore are actually quite complementary. The idea is that if you are deploying assets to produce hydrogen offshore, this is basically taking wind power and converting it into hydrogen, very simple terms. So you would ideally want to have that conversion equipment, which is very expensive, to be running consistently. So what we've been looking at is putting our type of storage technology between the wind turbine and the electrolyzer in order to give a more stable power input to the actual electrolysis taking place. We've done some kind of like feasibility studies and some research around this, nothing physically deployed yet, but we think it could be a very interesting application of the technology as well. And finally, a bit of like a niche application, but I think also quite interesting. As you'll see, and as I go through the slides, our technology requires like pressure vessels or pressure pipelines, so steel structures that can be pressurized. There's plenty of this offshore already in the form of like gas pipelines, and some of these are approaching end of life. I think most of them will be repurposed for hydrogen or carbon capture, but there is also the opportunity to repurpose these for hydro-pneumatic energy storage. So this is something, again, we've been looking into together with our collaborator and partners, Upscaling, looking at like different applications of how this can be deployed. And there are some interesting ones, I have to say. There are some cases where you can't use the pipelines for hydrogen or for carbon capture. So this becomes, another interesting alternative to repurpose the infrastructure. So enough about the, or actually one more slide about the why before jumping into the technology itself. This is a really recent development that we've been seeing, also kind of featuring on the like national grid and these kinds of grid infrastructure entities. So the existing model, and this is kind of just showing two different scenarios, the existing model with interconnectors is that you have a connection between two countries, and then you have a connection between the transformer for a wind farm and land. So it's kind of a really almost like fragmented system where these things are quite separate. And that means that the utilization of each separate connection depends on whatever is connected to it, which is not always the most efficient way of doing it. In fact, there's already now talk of like multi-purpose interconnectors. These images are actually taken from National Grid websites, which is all kind of stuff that's really being developed at the moment, where we can see that there's like a centralized platform, you have multiple wind farms that can connect to it, and then at the same time it serves as an interconnector. So you have a lot of wind blowing, you basically have the transformer harvesting all the wind and just kind of transmitting it to each country. But if there's maybe not a lot of wind, you can use that spare capacity to just transfer from one side to the other. What we think will be the next generation of this, and the way we see things developing, is that we will eventually start kind of connecting energy islands. Some concepts are already emerging, and then also utility scale energy storage, because it really ties into this idea of very expensive offshore infrastructure that needs to be maximized. So this is the best way we can use this, is just to have it used at its maximum capacity, and deploying part of the energy storage offshore will contribute to that and allow it to work more efficiently and be a more cost-effective overall energy system. So yes, now coming to actually the how and what is hydro-pneumatic energy storage. So the best way to explain this is to kind of imagine a rigid vessel, could be a large tank, but basically just a rigid steel structure. And inside the structure, we have a gas that is pre-charged, so it's at a relatively high pressure. And this gas could be air or nitrogen, so kind of like a safe inert gas. To charge the system, we supply electricity to a pump, and that pump is taking seawater and pushing it into this chamber. This gas is trapped, it has nowhere to go, so it is confined into a smaller and smaller space, with the water now acting as kind of a liquid piston. And that's basically the energy storage process. So we use water and incompressible fluid to manipulate a gas, which is a compressible fluid. And that's the storage part. To recover the energy, we allow then this gas to expand and push the seawater out through a hydraulic turbine, producing electricity. So it's very similar to pumped hydro, when you pump water up into a reservoir, but in this case, rather than work against gravity, we are working against this pre-charged compressed gas. So some key points is that it's a highly scalable system. It's actually best suited for a large scale. It's not something you can put in a car or in a boat. It has a high round trip efficiency, and I'll explain a bit more about this. And it's very well suited to the kind of shorter end of the long duration side. So it's like kind of on the 4 to 12 hour time scale. That's a good ratio between power and capacity. And much like a lot of offshore assets, it can really be designed for a long operational lifetime, which is also independent to how the system is cycled. So unlike, for example, batteries, where the way the system is charged and discharged impacts the lifetime, in this case, that's not an issue. It's a simple system, but there are two key things I like to highlight, which we've kind of protected through our IP. So one is this pre-charging. So I mentioned that the gas is at a higher pressure than its surroundings. And what this means is that we can deploy it in shallow water. There are other systems that use, that store energy offshore, but these typically use hydrostatic pressure. So they use the kind of natural pressure you have when you're underwater. It's very elegant concepts, but you do need substantial water depth to get the energy density up. So with this pre-charging process, we kind of reduce the dependency on hydrostatic pressure, practically eliminate it. And it means that we can deploy our system down to like 40 to 400 meter water depth. That's kind of the sweet spot. So although I'm showing a floating wind turbine in this illustration, this could kind of very well be a bottom fixed conventional wind farm. And that means that our solution can be co-located with bottom fixed wind. And the other point is, whenever you compress a gas, there are some thermodynamic losses in the process, which basically means that we do work, and ideally we want to get pressure at the end, but we also get some heat. That heat is kind of not something we really want, because we can lose that heat, or we have to store it. So what we do here is just we have a constant temperature system, and we achieve this by using the marine environment itself as a natural heat sink, which means that we only produce pressure, and then the pressure can be fully recovered when we discharge the system. I've got a bit more of a technical slide, but I was thinking to maybe insert this depending on the questions I get, if any related to this process. But in very simple terms, what we have when we charge the system is what's called like an isothermal compression. And when we then discharge the system, we have an isothermal expansion, and this leads to the high efficiency. So what we want basically is to get the AB profile as close as possible to the CD profile. So the compression and expansion are almost kind of superimposed, because the gap in the middle of that process, or the ABCD cycle, is the inefficiency. And then on the right-hand side, we have the actual cycle. These are things we've measured with our prototype, which are showing that they're actually very close together. So thermodynamically, it's a very efficient system. It's an important point because there are other losses which happen at the pump and the turbine. So if we don't have a very thermodynamically efficient system, then it's really just not going to be efficient overall. So this is the part that we've really focused on, and was the scope of our first prototype campaign. So this is a small scale proof of concept that we deployed in Malta back in 2018. We ran it for just over a year. It's really small, so something like a kilowatt hour of capacity, but it allowed us to measure this thermal efficiency and get some kind of real operational data to validate this idea that we had, which is basically if we submerge the process in the water, it will be just operate at a constant temperature, because the water is very good at absorbing and kind of recovering any heat that is produced or lost in the process. So this was our first proof of concept. There's some video on our website about the deployment, and it features quite heavily because it was really our first core project. But now coming to the actual technology itself, our focus as FLASC has been really the core hydro-pneumatic aspects. And as we've spoken to different entities that are looking at from floating wind to subsea oil and gas, it's like everyone has their own way that they would like to see this used. So we've shied away from actually delivering a hardware module and saying this is a FLASC product and just plug it into your system. So what we've opted to do is just look at different ways it can be deployed. And then we focus really on the energy conversion part, which is where we have the pumps, turbines, and control hardware. So this kind of like, red module. And then the pressure containment part, so the large tank, in simple terms, is something we want to be doing in a collaborative environment. So the first system that we're now working on, which is like a more upscaled version of our proof of concept, is like a number 3 system. It's going to be fully integrated into a floating wind turbine. And this is a project being run at our parent University of Malta. It's funded through the Horizon program, and will kind of target the small island application. In fact, the funding stream is specific to providing energy to small islands. And we are working with entities that have already established platform design, and we deliver the energy conversion part as a hardware module. And then another embodiment that we're working on, because we think it's really interesting, is something like a number 4 or a number 1, so basically an elongated subsea structure. So with this in mind, I'll now kind of come to the collaboration that we have with Subsea 7, and this is focused on developing this what we call now a power bundle. So I don't know if you're familiar with subsea bundles, but they are basically elongated structures that allow fluid to be transferred from one side to another. Typically, this is how they've been used in oil and gas in very simple terms. They are a very kind of robust technology with an established fabrication process and established, there's a site in Wick in Scotland where these can be built up to 7 kilometers. So what we're doing within this collaboration with Subsea 7 is kind of deploy our core hydro-pneumatic technology within the bundle. And what this means is that, in, again, very simple terms, it's kind of like blocking off one end and then just using the volume inside the bundle as a pressure containment system. So if we come back to the slide, it's this kind of long section that goes into the screen is the actual pressure containment part. And then the towhead structure is where we can put the energy conversion unit. So the pumps, the turbines, and then we just have an electrical connection. What we particularly like about this embodiment is that it fits very well with the offshore wind farm architecture. So if we look at a wind farm from above, we see, of course, the turbines, like imagine like little dots, but then between them, there's a lot of space that is needed for aerodynamic reasons to keep the efficiency high. And that's where the inter-array cables are laid. So a wind farm of like a gigawatt of power output would have, hundreds of kilometers of inter-array distances. And that's where we can deploy this type of solution that is fitting within that same corridor. And so superimposed on the wind farm, we now have like a grid of these power bundles providing megawatt hours or even gigawatt hours of storage. I actually have a short animation that shows this, this power bundle concept. So I'll just go through this, looking at first this offshore wind application. So yeah, this is like a conventional bottom fixed wind farm. And as you can see, there's some artistic license here in terms of the distances, just so we can see everything on the same screen. But as you can imagine, there's quite a long distance between each monopile and the other. And you can now see these kind of yellow tubes that are laid out, and that would be the pressure containment part of the storage system. Then at each end, there's a towhead. The pump and turbines are modular, so they can be kind of retrieved and serviced or replaced as needed. And then coming a bit more into the working principle, as I've already explained. So with the system discharged, we just have gas, and then we start pumping water. So this is like a subsea pump that is taking seawater and pushing it into the bundle. In this case, there's a pig that separates the water and the air. And as that water is being pumped behind the pig is kind of moving and compressing the gas further and further into the bundle. And as you can see, kind of the charging is increasing as the pig reaches the other end of the bundle. The top part is just containing the now fully compressed gas. So there's always some gas in the system, and now that gas is expanding and pushing the water in the opposite direction and allowing the energy to be recovered through a hydraulic turbine. So kind of now we have the electricity we put into the system, we're able to get it back, and it's just an electrical connection. As you can see on the right-hand side, it's just a cable. So it's agnostic to any power source, could be wind, wave, solar. It's really just about storing electricity. And then another application that I mentioned is, of course, these isolated oil and gas applications. So a floating wind farm now connected to an oil and gas platform. And this is now showing like a different system architecture with the bundles deployed as an array and providing utility scale storage for, in this case, an oil and gas application. So this is kind of features quite heavily in our collaboration with Subsea 7, and we've now secured some funding through UK base in order to do like a feed for a demonstration project, which will hopefully be deployed in the coming year. So we're just now going through more of the detailed engineering. One thing I wanted to touch on is the market. So this is, again, coming back to the long duration question and what does the market look like for these technologies? I have to say it's really early days, so there's a lot of questions on what kind of revenue streams these will generate, and specifically how will they make money, and that's the big question. But again, within this kind of McKinsey study, it's an important gap with a large installed capacity, depending on like different renewable energy system scenarios, and that means also a very substantial capex investment that will be needed over the coming decades. Again, as you can see, like 2022 doesn't even show up on the curve. We're really in the early stages of this. The first signals we're seeing are like funding bodies, as I mentioned, UK based, and also in the US, there's some funding that's being dedicated to these types of technologies. So kind of not batteries, not hydrogen, but this long duration gap. And we feel, we're very fortunate and really kind of excited to have gotten funding through the very first scheme that was launched in the UK for long duration storage. And this is also interesting because the funding is kind of not specifying offshore, it's just technology in general. So we're also very happy to see that our offshore solution is able to be recognized alongside the land-based systems. And it shows that the funding body recognizes also the need for offshore storage as a complement to offshore wind, which is the main cause of the variability. So we think that this is really a highly complementary approach. And on that kind of theme of like different technologies, this is a bit about the technology landscape. So there's quite a wide range of technologies that are available. Some of the land-based solutions include, compressed air, different variants of that. There's also some land-based hydro-pneumatic storage being done. There's electrothermal storage, gravity, liquid air, and there are also some other concepts that I couldn't include everything here. But the general idea is that this is really large infrastructure. It requires substantial space and sometimes repurposing existing facilities. So this kind of paints the picture of what our technology is comparable to. So when we talk about kilometers of bundle, we're not comparing this to like a battery in a container. And again, the land-based solutions will be a key part of this. But much like there are, onshore wind and offshore wind, we also think that there will be the need for offshore storage. And in the space, there's, as I mentioned, some concepts that use hydrostatic pressure. So like these large spheres that are storing energy by kind of earth being drained, and then you drain the sphere in order to charge the system, and then you allow the water to flood back in, and that is the generation part. Very elegant concepts, as I said, but you do need substantial water depth. So with our overpressure solution, as it's sometimes called, where we have this pre-charged system, we can deploy it in relatively shallow water below like 400 meters and have significantly higher energy density, which is why we think it's really uniquely positioned for co-location with offshore wind. And we're also quite happy to see legislation changing to favor like behind the meter storage, for example, in the UK with the CFD mechanism for subsidizing wind. In the past, it was really difficult to convince a developer to connect storage as part of the wind farm. But now legislation is really starting to favor it. And as I mentioned, also kind of tender requirements where they want to see innovation for offshore storage. And yeah, as a startup, this has been really exciting for us because we see a lot of interest from developers. It's been actually quite a bit, overwhelming sometimes because there is really not a lot of technology options that can be co-located with shallow water or bottom fixed wind. And yeah, to kind of give a bit of an overview of where we are now and where we're going. So this is kind of our timeline. We started with a concept. This was, as I said, like part of my originally PhD thesis, but with time we managed to build stuff and we started to see commercial potential. A big part of that was also, going out and talking to entities like Subsea 7 and seeing that there's ways to use this technology that we weren't necessarily aware of, like in oil and gas and these kinds of things. We early in the process secured the IP, so we had to have patents to protect this, and that actually allowed us to go and talk to various entities and see how it can be used. And one thing we also did quite early in the process is talk to DNV and get a statement of feasibility around like the various subcomponents. So what we see is that offshore, it's a great space to innovate in because it's a really interesting technology space, but it's also quite, it's not easy to convince people to take new risks with new technologies. So as innovative as our system is, it is using established subcomponents. So pumps, pressure vessels, turbines, valves, these are all things that have been deployed before. We're just kind of reconfiguring them to create an innovative solution. But ultimately, the core technology is very well understood, and we know how to maintain it, how to operate it, and how to install it. So yes, we've got then we did our proof of concept, but now we're looking at upscaling the technology. So we want to be able to reach TRL 7 next year. And this will be part of this floating wind project targeting small islands. The idea is to have a multi-purpose platform. We had an interesting design challenge here, was that it had to be a portable structure, so we couldn't put anything on the seabed, which is why we integrated it into the floater. And we're very this is in quite an advanced stage now. Our energy conversion part is being fabricated in Malta, and we'll start testing it soon. And this will give us the first wind turbine integration project, since the first system was really just standalone. So very much looking forward to this. And then, as I mentioned, we have received funding from UK base under the long duration energy storage competition, together with our partners Upsea 7, to do a feed for a demonstrator to be deployed somewhere in the UK. This is what we're currently working on at the moment. It's really exciting to start now diving into the details of this subsea solution. Thanks, and happy to take any questions or comments.